Probability and Statistics, Chapter 9, Section 2. We, in the first section, talked about, in general, tests about a population parameter. This one is going to be a population proportion. So, state and check the random 10% large counts conditions for performing a significance test about a population proportion. Perform a significance test about a population proportion. Interpret the power of a test. Describe what factors affect the power of a test. Describe the relationship between the probability of a type 1 error significance level, the probability of a type 2 error, and the power of a test. So, if we carry out this one, remember last section we talked about the basketball player claimed they had a 80% free throw shooter, and we said that we thought that his shots, the 32 out of 50 wasn't good enough to convince us that he was actually an 80%. Well, here we're going to use a number instead of just saying it looks pretty small. The simple random sample of 53 throws, he made 32. That gave us the 32 out of 50, 0.64, 64%, much lower than what he claimed. But the question is, does it provide convincing evidence against his claim? We have to perform a significance test of the null hypothesis, p equals 0.80. The alternative, if you remember, p is less than 0.80. P is the actual proportion of free throws the shooter makes in the long run. Okay, so remember back in Chapter 8 with the confidence intervals, we had 3 conditions. We have to meet those here also. Random, 10% when sampling without replacement, and large counts. The random usually is defined in the problem. 10%. Remember, 10 times your sample size has to be less than the population, or n is less than or equal to 1/10 of the capital N population size. And large counts, both NP and NQ, those are the 1 minus P sub 0, are at least 10. So the null hypothesis, H sub 0, P equals 0.80, if it's true, player's sample proportion of made free throws would vary according to a normal distribution. Mu sub p cap would be that 0.80. Standard deviation, sigma sub p cap is putting in the square root of p q over n. You get 0.0566. And you get this sampling distribution. Here's the 0.64 that was sort of like the same thing when we did the 400 sets of 50 shots, gave us something similar to this. But now we're using the exact normal distribution. Significant test uses sample data to measure the strength. Here are some principles. The test compares a statistic, in our case p-cap, calculated from sample data, the 32 over 50, and compare that with the value of the parameter, the 0.80, which is stated by the null hypothesis. Values of the statistics far from the null give evidence against the null hypothesis. But we need this test statistic so we can move things back to where we can check this a little easier, standardize this. And it looks familiar to the p-score, the z-score rather. The statistic minus the parameter over the standard deviation. So this would be the statistic, which is our p-cap, minus the parameter p over the standard deviation. That's sigma. So it says how far the sample is from the null parameter value and in what direction on a standardized scale. You can use the test statistic to find the p-value. We'll look at that in a second. In our free throw shooter, the sample proportion is 0.64, pretty far below the 0.80. Standardizing, we get the z-score, 0.64 minus 0.80, statistic minus parameter. Standard deviation, if you remember the square root of pq over n, 0.0566 gives us negative 2.83. So this top picture, this bell-shaped curve, is the normal curve located at the 0.80, and here's the 0.64. The p-value is the area of the tail here, from the 0.64 to the left. When you standardize that, now our center is 0, standard deviation 1 instead of the 0.0566. The negative 2.83 we got from before is that calculation we had here, the test statistic. The area from that negative 2.83 to the tail is the same, 0.0023, as we found up here. So we can do it either way. We've got a table, though, for the standardized score. So the shaded area shows the p-value. Corresponding area on the standard normal curve is the same thing. So the p-value is 0.0023. So if the null hypothesis is true and the player makes 80% of his free throws in the long run, there's only about a 2 in 1,000, that 2 in 1,000, 0.002, that the player would make as few as 32 out of 50. So, what do we do to do these tests for a proportion? State the hypothesis, also the alternative, the null hypothesis and alternative. Check the conditions. That's random, 10%, and large counts. Calculate the test statistic. Statistic minus parameter over the standard deviation of the statistic. And draw a conclusion. There's only two conclusions. Oh, this is the four-step process. There's only two conclusions we can come up with. So when the conditions are met, random, 10%, large counts, the sampling distribution of p-cap is approximately normal. So the mean is p, standard deviation, square root of pq over n. Z statistic. So this is really saying the same thing. A simple random sample size n from a large population contains an unknown proportion p of successes. To test the hypothesis, p equals p sub 0. This one like p equal to 0.80. You compute the test statistic. Z equals p cap minus p over sigma sub p. And that's the square root of pq over n. You might get something larger, smaller, or not equal to 2 tickets. If it's two-sided, then not equal to, then you get a sample. You got to be careful because on your calculator it'll give you that observed value of p cap. That should be p cap here. Find the area in both tails for the p, because the alpha is going to include both the p's. So we learned about confidence intervals in the last chapter. Why do they give more information? Significant test just says either reject or fail to reject. If we reject, we're left wondering, okay, what is the actual proportion? A confidence interval might shed some light on that issue. If Taeyeon found 90 students with a simple random sample of 150 said that they had never smoked a cigarette, the number of successes and the number of failures in the sample are 90 and 60, so we can proceed with calculations. Our 95% confidence interval, p cap plus or minus z star, square root of pq over n, remember that, gives us this interval 0.522 to 0.678. We're 95% confident that that interval captures the true proportion of students we would say they never smoked. So not only do we say, okay, the 90 out of 150, the two-sided test is really the same as this 95% confidence interval, with alpha being 0.05. So if we do this two-sided test with alpha 0.05 and the 1 minus alpha, both of these, the confidence interval, a 95% interval, the 100 times 1 minus alpha, the 0.05, gives similar information. But let's go back just a second. But this would just say that they either reject or fail to reject. And our confidence interval, if, so what is 90 over 150 as a decimal? Well, it's 9 over 15, which is 3 over 5, which is 60, or 0.60. That falls in this interval. And when we do the confidence, or the significance test, we'll find out that we failed to reject. So we at least know that 0.60 is in that interval for a confidence interval. The type 2 error is also called, it's part of the power of the test. If alpha is the type 1 error, beta is a type 2 error. The probability of making a type 2 error depends upon a bunch of factors. Part of that's with the number of people in the sample and some other things of what you choose as your parameter that you came up with. We're not going to do a lot of this in this course, but it's harder to figure this out. The biggest thing to look at is this picture. If 0.80, or 0.08 rather, is this situation, and the error here, the type 1 error is alpha 0.05. Now, notice this green line. Suppose we assume that instead of 0.08, it's 0.11 someplace in here. We get a new picture. And now you get this big area. This area is 0.7517. This is the power of the test. So how did you choose 0.11? That's a good question. Maybe that's another one that you would get from your information because you know the job so well, instead of the 0.08, which is over here someplace. But that 0.75, the power of the test, tells you that we'd correctly reject the shipment about 75% of the time. This tells you how would you be correct to reject it. Anyway, it's pretty hard to figure out the power of the test. So what you really need to do, instead of trying to figure out beta, is to figure out what alpha is. And here's an example. 11% of products produced by an industrial process over the past several months have failed to conform to specifications. The company modifies the process, wants to reduce the rate of nonconformities. A random sample 300 items in a trial run. Modified process produces 16 nonconforming items. Do these results provide convincing evidence that the modification we made is effective? What's the null hypothesis? Well, let's see. It's got to be the P. It's got to be equals. But what is it going to equal? 0.11. 11%. They didn't write it as a number, so it's hidden in there. That's the null hypothesis. The alternative, we want to see if it's less than.